пару слов о профессоре Стоопе. Он работает, один из немногих, там, по-моему, порядка 5 или 7 faculty members Institute of Neuroinformatics в Цюрихе. Исходно, your background was applied mathematics, correct?
Yes.
Yes, and then потом он переключился на физику, достиг больших успехов вот в конкретных физических приложениях и примерно с 1996 года работает вот в этом институте нейроинформатики в Цюрихе, занимается очень многими проблемами. Вот одна из проблем, по которым работает профессор R.Stoop, будет доложена сегодня. Please.
Hello, all together.
Is there mics are only there
is there a pointer? Yeah. My voice is too loud anyway. Okay, so it's great to be back in Russia. Thanks very much for the invitation. I appreciate it a lot, and I enjoy a lot being back here. Normally, I'm not in Moscow so much, but I appreciate being together with my colleagues very much, and thanks for the invitation. Coming back to Russia, I felt silly to come up with a theory and bring some more water to the ocean, to the country that had so many great theoreticians. So I decided to report a little bit on the country where I come from and what we do. We are great watchmakers, as you probably know. And so I try to give you the point of view of this whole thing from a watchmaker's perspective. I look at a small system and try to understand how it works, how the human mind works, and I feel that I can be able to deliver many illustrations to the talk that just has been given from a practical point of view. In my perception, what is in this hype about the human brain project and all these things, I think it's being a conservative Swiss, I think it's exaggerated. So I think we should not forget that the basic principles of science are mathematics and physics. And what I try to do is I look at the human brain as an onion, and I try to peel off from the sensory point of view. I look at the senses here at the hearing system, and I try to peel this onion as much as I can from the point of view of physics. Everything that we can explain by means of physics, we don't need to give away to neuroscience or whatever. Maybe there is something left in the end. I think we will not have time to get rid of all the shells, but then there is something like the mind, I suppose, or individuality or religion or whatever. But from my point of view, I'm interested into seeing what physics can contribute to the understanding of the human brain. So I will talk about the mammalian cochlea, neural networks that are involved within the mammalian cochlea. I will show you that we get neural avalanches in the cochlea. And then this is probably something that I will not have so much time to talk to, but I invite everybody. I will stay here for some more time, and we can have any time a beer or tea, if you insist, together. So this is work together with some students of mine. One part of the work that we do, we are interested in more application parts. Also, I'm a theoretician, like bioinformatics, clustering, spatial temporal signal characterization, computation, network analysis, behavior analysis. What does the fly do when it makes courtship? How do you be able to say that information is being transferred and how you measure this, things like this. Then we have symbolic dynamics and languages, abstract dynamical systems. This is where I come from partially, and then we do statistical mechanics of biological systems. So here in this particular talk, I want to take you on a journey to see how do we hear and why do we hear the way we hear. And I will show to you that the key for understanding hearing is nonlinearity, that is within the physical systems. And then we are now in this network age of physics, and from single frequencies to the cochlea is exactly such a process where we go from individual systems to a whole system. And then I will show you how, using physics, you can build a cochlea from scratch on very simple principles that outperforms any artificial cochlea that exists. This is not a boasting statement. This is just the truth. Also, I'm not an expert in cochlea making. Our cochlea is at that time certainly the best cochlea that exists. And this is just not a self-advertisement, but it's an advertisement for physics. Then I will show it to you how we can benefit from combining physics with a real experiment. So if you have a theory, you should have an experiment. You should have a hardware that verifies what your claims are. And you can even benefit from it, as we will see. Then we will go into the curse of nonlinearity. I'll give you an example of within hearing that shows you how complicated the brain must be because of these nonlinearities. And then I'll show you that power laws in the cochlear network exist, similar to these neuronal avalanches. And I will only be able to briefly mention what this means from the point of view of dynamical systems interpretation of the brain. And so with these power laws, there is a notion of criticality in the brain involved. And then the question is, what has learning to do in this context? And I will show you that the learning does nothing but drives you away from criticality. So what do we hear and why? And this is like a soccer game in around 1850 in Germany between Dresden and Berlin. Here we have two stars of the team. One is Ohm, the guy from Ohm's Law, and the other guy is a young, brilliant person. He looks much better than this one. He's Seebeck, and Ohm looks particularly pissed because this young guy showed him that he made an incredible error by trying to explain how people hear the way they hear. So then this is the starting point of this famous controversy between Ohm and Seebeck. And it started all about the question, what is the physical description of the sensation of the pitch? The pitch is the height of the tone that we hear. And why do we hear the height as it is? For pure frequencies, this is not the question, but when you get more complex tones, this is really an astonishing fact that we hear a height of the tone, first of all. And then what we hear is really difficult question to explain. And Ohm thought that it would be simply a matter of Fourier analysis that developed at that time. But Ohm showed him that this is not the case. And Seebeck said, wodurch kann über diese Frage, was zu einem Ton gehört, entschieden werden, als eben durch das Ohr? How else can the question as to what makes out a tone can be decided other than by the ear itself? So you need, what the content of this phrase is, that you also need to take into account the physical properties of the receiver and of the biology. This is where physics and biology meet. Now, the mammalian cochlea was looked at the time of Ohm as a frequency analyzer. Here you have the unrolled cochlea, and here this is the basilar membrane. That is a membrane that floats within fluid in the cochlea. And when a sound arrives here at the cochlear base, there is a wave, a shallow water wave running down the cochlea till the point where it gets the highest excitation. And this is the relative amplitudes. Here we have the high frequencies, and here down we have the low frequencies. So high frequencies that get killed after running very small distance. After that generation, low frequencies travel longer along the cochlear duct. And this is the idea of the cochlea, and this is a movie that has not been created by me, but it's so nice that I want to show it nonetheless, in particular because it's wrong. So this is the cochlea here. Now we are going to unroll it. Now you have an elongated cochlea. And now you will see here the input. This is the water wave that goes down here. The highest tones are here, and then everything else is superposition. And this point of view is completely wrong. This is not what the cochlea does. But this has been the basis of all the physics of cochlear implants and all these kinds of things. The music is nice nonetheless, even though the model is wrong. So at this point, I just make a very brief detour. Why do we deal with sound? Why do we deal with periodic signals? Why are periodic signals so important to us at all? Now, the majority of the systems, we have learned this in the last 40 years, that we look at, that may actually be chaotic. But due to limitations in the form of weight, for example, or other constraints, these chaotic systems are constrained. And it's a very simple and universal statement that due to simple limiters, so when you limit the phase space around here by imposing limitations on the system, you will select out of the chaotic motion the most complex possible periodic motion. And this is actually why you have so many periodicities. Look at a young horse. It will do all uncoordinated movements. But when the horse becomes a little bit older and starts to have a belly like I have done some time ago and still have, then you make more periodic motion. And when you have a very heavy load on the back and you move on the, towards the mountain, then you don't jump in all possible directions of freedom, but you take one step after the other. This really explains the gaits that animals have without any control needed. It's a very simple theory of limiter-induced chaotic control. You don't need a very complicated controller. Who's interested can look up these papers here. There sometimes go. So here is a chaotic parabola for those who are familiar with this paradigm. And if we impose here a limitation that depicts or implements a sort of a load the animal has, we go from a chaotic movement to periodicity 4. If we lower the limitation or increase the load, we get to simpler motion here, periodicity 2. This is just to explain that periodicity is not an accident. And this is why people start to listen to periodic sounds and are interested in pitch or sounds. Now, the history of how people thought it would work is really interesting, and I hope that you give me some.
Ready mic. Probably not everybody hear you. Just speak to mic, the microphone.
Okay, it's not loud enough?
No, closer to, no, closer to.
Okay, I can do that if I don't want to frighten you. Yeah. I'm usually too loud, my wife tells me. The history is really interesting. 500 years before Christ, Empedocles started to have develop a theory of the hearing, and he was convinced that air would play the major role in the whole story. Then 200 years after Christ, Claudius Galen in the Roman Empire, he discovered the nerves within the cochlea. 1550, the first book arrived about hearing, De Audibus by Koiter, a Dutch. Then Perrault, the French physicist of the pendulum, he was convinced that the air and the hollow cavities in the cochlea, that they were filled with air. Also, always there was water coming out of the cochlea, but they were convinced that it must be air, because the old Greek had the theory that matter only communicates with the matter of the same kind. So air would communicate with air and water with water, but not air with water. And this was carried along till Schellhammer, a German physicist and biologist, started to ask the question whether this really was the case. And Cotugno, an Italian, in 1760 really came up with the proof that the cochlea is filled with a fluid, with water, essentially. Then how the hearing system would work, there was a professor in Basel, Switzerland, who looked at the cochlea, and he was convinced that they had something to do with resonance. Otherwise, he was a completely reasonable person. But here he thought that he had resonant cavities, and Kramers had a strange theory of strings, and then there was the telephone theory of Thomas Young. Helmholtz applied then, as the first guy, Ohm and Fourier theory to the cochlea, and Johann Müller then discovered the biological part of the cochlea. And von Békésy, then he was an Hungarian living in Switzerland for a long time, or being educated in Switzerland. He then developed a model of the passive cochlea, where he used rubber models. In 1947, people found that this was not enough to reproduce the behavior of the cochlea, and they claimed that there must be active elements, and these are the nonlinearities that we will talk about. The key for understanding hearing is nonlinearity, and it's connected to a concept of theoretical nonsense, as I call it, or that we used to call it, to the small signal amplifier. The small signal amplifier is something that Wiesenfeld brought up, but I'm pretty sure, or completely sure, that the Russians knew it long ago and also published it, but I'm not so familiar with this literature. Any system close to a period doubling bifurcation, this was in the first PRL, formulated in this way, can be used as a small signal amplifier. So when you have a system that is close to a bifurcation, a little bit of perturbation leads to huge excursions. We all know this in times of revolution, for example, we have such a situation. Then all kinds of things can happen. And so if you have whatever system close to a bifurcation, it will react because it doesn't know in what state it should be, whether it should be the behavior below the bifurcation point or above the bifurcation point. Will be amplifying this input greatly. And here is a picture of this Wiesenfeld period doubling system, and here we have a pole of the amplification here, and here is the frequency line at a certain frequency, and the detuning here we get of the stimulus, of the perturbation, we get a huge reaction. The We then showed that this also happens in a Hopf bifurcation. If you take a Hopf bifurcation, it's true, as I said, for any bifurcation. And this is the behavior of a Hopf element. The Hopf element is actually, behavior is connected with some neurons that go from quietness into periodic firing. The other is the saddle node bifurcation. In the hair cells that are within the cochlea, we deal with Hopf bifurcation. And this is the behavior of the Hopf bifurcation as a function of the frequency of the perturbation. Here we have the amplification, and this is the distance here to the Hopf bifurcation point at 0. You see, if you are below the Hopf bifurcation, you have still the Tsar ruling the country. The perturbation is nonetheless very strong when you put it into the system. And here you have the same at the fixed Hopf, Andronov-Hopf parameter. And here you have the input that you put as a perturbation. And here you have the amplitude. And you see these huge peaks. And this is called the small signal amplifier. You have a small signal, and the smaller the signal here, the higher it gets amplified. And if you put in a very strong signal, it does not react. Actually, our ears can hear down to the Boltzmann noise, and nonetheless, we can hear a supersonic jet. This means that with a measurement device that you use for electronic circuits in your cellular phone, you can also go to the over-country power lines and measure the power there. It's incredible. Now, there is biological evidence other than the cochlea that this principle is a universal one. And here is the Drosophila that we know very well. And the Drosophila has scattered all over the body whole types of sound antennas. So it has an antenna, or it has a so-called chordotonal organ, which is a sort of a drum. They all stem from the same genetics, and they all work very much the same. Here, just a free hair cell, and here is the chordotonal organ. It's a hair cell that is just between two plates. And these two construction mechanisms, they are also in the cochlea, as outer and inner hair cells. So you can really prove that the antenna of the Drosophila is at the verge of a Hopf bifurcation by putting chemicals into the Drosophila that pushes it across the Hopf bifurcation point, and then it starts to oscillate. And then you can analyze, because you have an oscillation, what type of dynamical system it is. This is a work that I did with people from Saratov, the group of Boris Bezruchko. And here we found that these behaviors here can best be approximated by a generalized Van der Pol oscillator. And this explains everything, and it explains in particular that in this area here, active energy is put into the system. That means the system does not just react on the stimulation, but it actively amplifies the system. And this is really a nice work. This has been published in Europhysics. Now, an animal wants to understand or pick up different frequencies because it has different sizes of predators or prey. So it will be interested in hearing different sounds. So we already are now from a single amplifier to a whole system of amplifiers, and they could be organized in different ways. Here I show you a scaling of things. Here are the best audiogram frequencies. Here, for example, is the basilar membrane in millimeters, the best audiogram frequency here. Or here is the body weight and the brain weight or the cochlea weight. It's all scales. So the bigger you are, the more interested you are in hearing sounds that come from your conspecifics. Or, so hearing scales with the animal size, and we have a coupling problem. The Drosophila has not got so many different ears. If the humans wanted to have different ears, we would have more than 2 ears. But we have a brain, and the brain really replaces the high number of ears that we would need to have in order to be hearing as well as we are now, if we had single detectors for everything. So the Drosophila solved the problem by putting the different ears at different locations all over the body with the largest possible distance. But this is only possible if you don't need to hear too well, if your discrimination does not be too strong. So here, for example, we have detectors for different frequencies of sounds. And so what nature decided to put it on one plate, centralize it together here. But the problem that we have now is that these these detectors, they are nonlinear and they are in close vicinity. So they start to interact. And here we have a picture. These are these hair cells that I plotted in an abstract manner. And if you can't hear, if you're deaf, then your cochlea looks like this here. These are the outer hair cells. These are the amplification things. The inner hair cells, they are more robust. They just pick it up, the sound. But these are the active amplifiers, and they die during the course of your life. And there are not so many, actually. And you can't regrow them. So what you can do now from a physics point of view is you can analyze what you know about the physical systems. You have fluid dynamics, you have statistical physics, and you can devise, or you come forward with an equilibrium equation for the energy density in the cochlea. And this is an amplification term and a dissipation term that works on this energy that you have. And you can then specify this by putting it into an energy balance equation that is very general. And then you have an equation with the energy density, the group velocity here, the dissipation, and the amplification. That's it. And now if you go into the details, I'm not pretending that I want to show you the whole theory of the thing, but I want to show you how physics is important in understanding the hearing. For example, you have the energy balance equation here, then you integrate the whole thing here, then you have the wave amplitude with the basilar membrane stiffness term here. You have the passive traveling wave you can select, and you have to find out these terms here. And then you can put here, you find out that the dissipation in this fluid must be of this form, and then you see that you have dominant viscous losses, and the kinematic friction can be thrown away or neglected. And from this, then you can come up with a surface wave of the cochlea where the group velocity has this form here, and this is then essentially a dispersion relation that gives you a relationship between the dominant wave frequency and the place along the basilar membrane that leads to this amplification, and you see here the pole at this point. So this is fluid mechanics, but what is important is this amplification term A that we're looking at here. And this is what is provided now by the nonlinearity. And this close to a bifurcation point, if you have a Hopf bifurcation, then the response is the forcing to the power of 1/3. And this is why we know that in the cochlea we have a Hopf bifurcation, an Andronov-Hopf bifurcation, I should say, sorry. Then this is the characteristic, and now we have many such characteristics, and the question is how to couple them to get a good response. Here, that is the natural response. This is what we did when we are subcritical, then the people at 0 Hopf bifurcation point, and this gives you a jump here that is on biological. And we then decided to change our theoretical models into hardware. Here is one place. So then we dissected the cochlea into different parts. And this is the print, and this is now a cochlea here. And what you see here is these are the data that are from chinchilla. So all the mammals have the same response of the cochlea, by the way, and the same building principle. So this could also be a hedgehog or whatever. And this is our system here with different input strengths and at different Hopf parameters. And you see that here you have this little bump here. This is a discretization effect. So when you take enough of these sections, you can get an incredible amplification that is even better than what the human ear is able to do. Then this as you go along the cochlea, this profile changes a little bit. This is what we know from measurements, again, biological measurements. And the test for the system that you have is that it should change in the same way as the cochlea does in the biology. And it really does. It gets, it changes here exactly in this way, and also the dynamical response to the most complicated signal like the click is exactly of the same form. Then you can see, I told you that we have nonlinear elements and there are distortion products or combination products, and you can rescale this suppression, so nonlinearity can lead to suppression or to combination. We have these observations in the cochlea, and you can then come up with an effective Hopf parameter for suppression and for combination tone that really describes all experiments extremely well. The result of this is then that you have now a cochlea that you can compare to what people have measured how we hear, the humans hear sound. And these were here standard models of including nonlinearity of hearing, and the black dots were experiments by Smorenburg, a Dutch physiologist. And what you can see here is for this frequency here, so you have these two frequencies. One is F1 and the second stimulus is F2. So you have this effect only for particular complicated tones. And you see, you hear something that is completely away from prediction. Actually, when you hear a sound, what you would think usually is that you hear the basis frequency. But even if you can now manipulate with the computer frequencies, do Fourier analysis, you throw away the basis frequency and you still hear the same sound. This is the phenomenon of the missing fundamental, and this you can explain. Now, when you think about how this comes to reaction, you can look at the signals in frequency that are in the cochlea at the different sections. And what you see is that if you put in two signals, you get these so-called combination tones here at places that you can predict by theory. So when you put this a simple complex, I mean, it's not just one frequency and the overtone, but two frequencies, for example, and their overtones into the cochlea. What you see is these are the inputs here. Here we only have two frequencies, not even the overtones. And at section 6, you have a response at really crazy frequencies that you would not expect from linear theory. And then you go further on to section 13, and then you see this here. And when you go along the cochlea, you see that the cochlea is excited at presumably unpredictable places that seem to have very little to do with the frequency you put into the network. And this is a stimulation of a neural network that responds in an extremely complicated and complex way here. And this you can... So here are the combination tones, and if you want to make a statement, you have to again, you have to again see that that these combination tones have the same scaling as in biology they do. But if you go now along the cochlea, through the cochlea here, you see these combination tones emerging all along the cochlea. Here is the input that would give you the input frequencies, 3 input frequencies. Here you are a little bit further down the cochlea, and then when we go down the cochlea, you see that the spectrum is dominated by frequencies that have apparently nothing to do with the input. Now, here, these are the combination tones. These are the Hopf cochlea. These are biological data because it has a lot to do with scaling. We have to make sure that we have the same scalings here and there. And I should hurry up now, probably. So there are 2 pitch shift effects depending on types of the signal that you put in. The first pitch shift effect is one that for which this phenomenological formula exists, and you can derive it from theories of nonlinearity that exist, and these are these lines here with the red bars, and the red bars come from how you choose k. You can take k or the next k, whatever, because these are the 2 frequencies that you put into the system. And yet our system really behaves completely different to perception. When you look at this, when you put the sound into the cochlea that corresponds to the theory that should give you this response here, you really see that theory and measurements are the same. But when you give a more complicated, complex sound, you see that you really need to have for the complex sounds this relationship here. And we were able to show that this is really an effect of the hydrodynamics, the friction in the... So the sound that you hear has to extremely to do not just with the signal that comes in, but with the physical system by which you hear it. And this is now how from the cochlea to the inner hair cells, the whole system goes through. Normally you would say, okay, we have these combination tones, why don't we filter them out? But the nature really decided to leave them in and to work with this system. And this is the input sound. It goes through the cochlea into the auditory neurons. And this is what you get. These are the frequencies at different, here the cochlea output, the inner hair cell output, the neuronal histogram of firing intervals. And you can really model this, and it's actually one of the nicest examples of stochastic resonance that is used by the inner hair, by the auditory nerve, the nerve that leads from the cochlea to the brain, to maintain all these idiotic combination tones that you generate artificially on the level of the cochlea, which is completely different and opposite to what the technician would do. He would filter the signal and send the filtered signal upwards. This is not what the human brain does, and here is the proof for the stochastic resonance. Only when we put in the noise that we have at the connection between the cochlea and the inner and the auditory nerve, these synapses are known to be very noisy, and only if you put in the right amount of noise here, you get the peak of the stochastic resonance that really tells you, gives you the best representation of what people are known to hear and what your system, based on physics, is able to produce. And here you have the same story again with the same stochastic resonance principle. And here is, if you increase the noise, you're here far off, you don't get the right frequency, and then here this bump develops, and this bump remains until it is destroyed if you put in too much noise. So the second pitch shift, this is what people could not explain, is really a physical effect and has nothing to do with the brain. It was, for 20 or 50 years, it was claimed that it is neuroscience, matter, and whatever, but actually it's nothing but physics. Absolutely nothing. And so the pitch perception really happens in the cochlea and not in the brain. And I think that this is an important message. This is the one piece of the onion. And now we can look at the nature of the cochlear network. So there is, in fact, a cochlear network. I showed you that you have activation along the cochlea. And here again is this activation profile. And you can now think of what excited elements here contribute to later, down the cochlear duct, excited elements later on. And so you put in here an input, and this one gets excited, and this one is excited, and that one. And these excitements sort of transfer to later sections. Of course, this is only a coarse grade model of 30 sections, but we have actually in the cochlea a finite number of outer hair cells. So this is, if you put in another input, you see that the network is completely different and the activation here is different. So you can look at the network where you have one network that is excited and another network is excited. These excitements have very little to do with the input, but are just a sort of a result of the nonlinearity. And what you get by these things are if you put in pure tones, then you get on a logarithmic scale the same areas of excited hair cells. But if you put in complex sounds, then you get a sort of complex response fields here. These are the two frequencies that you have. And this is on section 2, and that's section 20. It changes as you move along the cochlea. So we have a complex network of activation, and the pitch actually that we hear is a sort of a global characterization of these excitements that you have. So pitch is a global, we can show this. I do not really put it out on the last line here. But pitch is a global characterization of this excitation pattern. And I think if we want to describe the brain, this is what the cochlea tells us to do. It's like a fractal dimension that describes a complex system with one number, or if you have a family of fractal dimensions or Lyapunov exponents, finite time Lyapunov exponents, this is what it does. And the pitch is, in this way, physical and not neuronal. What we observe, if we put in random sound levels...
5 minutes.
Yes, I will make it within 5 minutes. Then here is the frequency along the cochlea on a logarithmic scale. And what you see is, if you randomly now stimulate the cochlea, is that you see power law activation distributions. Now, most of you will be familiar with the theory of Bex and Plentz, who observed power laws activations or neuronal avalanches in the neocortex. And they made big stories about it. And this is really a very fundamental behavior of biological networks that process information, that you have these power laws of activations here. Now, if you go back to this networks, you can also look at the size of the network that the stimulation generates. So you take two tones, this makes a complex tone together. You put it into, sometimes you excite a small network, sometimes you excite a larger one. And if you do the size statistics, what you see, that you see a power law with exponent -1/2, and this is the percolation exponent at critical point. So this is the cochlea is really at critical point if you put in stimulations that are in the middle of that what the cochlea likes to have. If you put in too loud or too weak sounds, this changes a little bit as here. So what happens now if you learn? So if you can depict this as when you take away two Hopf parameters of these 30 elements, Hopf elements, away from bifurcation point. And in this way, you can really listen to sounds. This is what the neural system does. And what happens with these power laws, they change here. So hearing or learning or listening, it's all the same, kills you power law. The power law is the basic fundament of the fundamental state of information processing in a multi-usable neural system or in a system distributed for working with information. And when you tune down some elements, and this is what you do when you learn, normally you increase the weight. Here you decrease the weight, but this is exactly the same. And biology does decrease. This we know from biology. Then you really can listen to sound. And this network that we have here then shrinks towards a sub-network here of things that you want to have. And the edges and the nodes, as a function of detuning, they go down, and the small world characteristics also go down. So you move away in your small world network characteristics from small world to more specific and dedicated one. And this is in correspondence. So we can show mathematically by means of hard dynamical systems theory that power law distributions characterize the fundamental ground states of computation in network. We need the thermodynamic formalism of chaotic system to prove that. This is in correspondence with the complexity measure of prediction that Diane Bunimovic and my eldest son have developed, which is highest for these distributions for intermittent systems, and the computation measured as the degree of removal of this difficulty when you put the information through these systems is smallest. So it's really the ground state in this multi-purpose network, and if you teach this network, this drives the network away from this state, so the complexity of prediction, what the system does next, decreases, and the computation increases. This is the deeper meaning of these power laws that you have in the neocortex as well as in the cochlea. And the cochlea, of course, is much nicer because you have controllable conditions in comparison to the neocortex. And this is then other things that you can use to really tune the system to hear. So we applied it to separation tasks.
I'm sorry to
I'm
say,
finished.
but time is over. Yeah.
I'm finished. So the cochlea is a showcase, and we have a US patent for this cochlea that we devised. That was completely, for theoreticians, completely unexpected. Also that we were able to build the cochlea. And these are some of the papers that we published in this area in this field. And so if there is a surgeon who wants to implement such a cochlea as a cochlear implant, I will be happy to collaborate with him. And thanks for the invitation and attention. And last but not least, it was great to be back in Russia. Thanks for your attention.
Ну, хотя время кончилось, один короткий вопрос у нас единственный. Не говорящий по-русски докладчик. Есть короткий вопрос? Пожалуйста.
Thank you for the very exciting report. I didn't know about this mechanism, and now I am. So thank you for it. My question is a little bit futuristic. If we know now the mechanism of hearing and that all the reasons of hearing in cochlea, yes? So could we change the mammalian cochlea genetically to hear another alternative frequencies?
Yes, we actually published a work that is not listed here. Since we know all the mechanical properties and everything, and we know that hearing requires intact connections from the brain to the cochlea and active amplification. So what all you need to do is to shift the frequency distribution along the cochlea. And in this PLOS in 2007, we really showed how if you were able to change the basilar membrane stiffness at places, or to put additional weight to the basilar membrane, you could get an intact hearing. Of course, you would also need to learn again, but you would need everything, and you could listen again. This is the big thing, is to be able to listen.
So people potentially could hear ultrasonic sounds, for example, yes, or infrared sounds.
Oh, that is a little bit. So I was talking about modifications of the normal human hearing system between some 100 and 20,000 hertz. But yes, if you change this general principle, you can use this method to hear ultrasonic sound. If you put in all the frequencies in these sections, there is no problem at all.
Thank you very much.
Or you can use it in astrophysics, for example, if you want to.
Thank you much. Sorry, we have no time. Yeah, so let's поблагодарим докладчика.